We talk a lot about fundamental particles, but the Higgs boson, that's like the rock star of the particle physics world, right? I mean, this is the one that supposedly gives everything mass.
Right.
But what if there's more to the Higgs than we thought? What if there are these like hidden particles out there influencing it in ways we haven't even begun to understand?
Well, that's the really exciting part about this paper we're diving into today. 4 generations and Higgs physics.
Yeah.
It introduces this really cool concept, a fourth generation of particles.
Okay, a fourth generation. So for our listeners who haven't quite gotten to that chapter in their physics textbooks yet, what are we talking about here?
So imagine you've got the periodic table, right? All those elements neatly organized. We've got our 3 known generations of particles, quarks, leptons, all the usual suspects. But this paper is saying, hold on a second. What if there's a whole other section of the periodic table we haven't discovered yet? A fourth generation of particles that just might be lurking beyond our current ability to detect them.
So it's not just that these particles are difficult to find. This paper suggests they could completely change how the Higgs boson, this fundamental particle, actually behaves. We're not just tweaking the model here, are we? It's more like redrawing the map entirely.
You got it. And what's even wilder is this particular arrangement of fourth-generation particles they propose. It wouldn't necessarily contradict everything we already know about the universe. They're talking about a very specific set of characteristics that, if true, would just make the Higgs act in ways we never even considered.
So the universe is basically playing hide and seek, and we might need the Higgs boson to help us find what's missing. Where do we even begin to look for something that might not even interact with the world in the same way as the particles we already know?
Well, that's where things get really interesting. Experiments like LEP2 have helped narrow down the possibilities. It's like they've created this cosmic sieve, and by smashing particles together at incredible speeds, they've been able to rule out certain mass ranges for these hypothetical particles.
Okay, so LEP2 gives us some boundaries, but it still seems like we're trying to catch a ghost. We might see the footprints, but actually grabbing hold of it is a whole other story. What about other experiments like the Tevatron? Didn't that push the energy levels even further?
It did, and the data we got from the Tevatron, especially from the CDF, the collider detector at Fermilab, that put even tighter constraints on these potential particles. Specifically, we saw a more solid limit on the U4 quark.
And not the D4 quark. Why is that? Is it just really good at hiding?
That's the big question. The paper suggests that this D4 quark, it might interact with other particles in a way that makes it incredibly difficult for us to detect. It's like trying to hear a whisper in the middle of a hurricane. The signal might be there, but it's completely lost in the noise.
So we're dealing with potentially massive particles that are basically experts at cosmic camouflage. What's the paper's explanation for why these fourth-generation particles have managed to stay under the radar for so long? What are they doing differently?
Well, to get into the nitty-gritty, it suggests these particles could be interacting incredibly weakly with the matter that we're used to seeing.
Okay.
It's like trying to catch a shadow.
Uh.
It's there, but our usual methods just can't seem to grasp it.
So we've got these masters of disguise, these particles that might be lurking just out of reach, but let's say we do manage to find them. The paper hints at some pretty wild implications for the Higgs boson, if that happens. So it's not just about finding these particles, even though that would be a huge discovery in itself, right?
Oh, absolutely.
This paper is really saying that these particles could completely change how we understand the Higgs boson.
It really does, yeah.
So we spent a lot of time talking about how hard these particles might be to find, but the paper really digs into what happens if they are out there. How would these invisible particles, these masters of disguise, actually affect something as fundamental as the Higgs boson?
Well, it all kind of boils down to this idea of the golden mode. Have you heard of that?
Okay, so remind me, golden mode. I feel like I should have memorized that chapter of the particle physics textbook, but it's a little fuzzy.
It's like the holy grail, right, of Higgs hunting. It's this specific way that physicists expect the Higgs boson to decay most often.
Okay.
And it decays into a pair of Z bosons, which then further decay into 4 muons. And it's this very distinct signature that we look for in the debris of particle collisions.
So it's like the Higgs boson's fingerprint. We see this specific pattern of decay, and we know that's our guy.
Exactly. You got it.
Yeah.
And the thing is, if these fourth-generation particles exist, it would amplify this golden mode signal, so it would be even more pronounced.
So it's like turning up the volume on the Higgs boson's fingerprint. We're going to see it even more clearly, potentially.
In a way, yeah. But here's the thing. While the golden mode gets amplified, Other methods that we use to search for the Higgs, like something called weak boson fusion, become less effective.
Hmm.
So it's like we're gaining clarity in one area,
Right.
but then the landscape around it is kind of shifting, and it makes it even harder to navigate.
So it's like we're getting closer to the treasure, but the map is changing.
Exactly. And that's the real detective work that comes in, right, for physicists. Because this paper is essentially saying, okay, here's a new set of clues, here's a revised map, but we have to learn how to read those and adjust our strategies accordingly.
So it's like we're realizing that maybe the treasure isn't buried where we thought it was, the map's been updated, but now we need new tools to actually find it.
Yes, exactly. And it's not even just about the golden mode. This paper also suggests that if these fourth-generation particles exist, we might start seeing something truly bizarre.
Yeah.
We might see the Higgs boson decaying into pairs of particles that have the same charge.
Wait, hold on. That sounds a little, that's not right, is it? That's like saying you saw a magnet that had two north poles.
You got it.
It doesn't work that way.
In the current model of particle physics, that kind of decay is almost unheard of. But the presence of these fourth-generation particles, it could flip the script. It could make this extremely rare same-sign decay of the Higgs boson much more likely.
So not only are these hypothetical particles messing with how we find the Higgs, they're potentially rewriting the rules of particle interactions as we know them.
That's the incredible thing about theoretical physics. Even the most outlandish ideas, if they hold up to scrutiny, they can have these really profound implications for how we understand the universe.
It makes you wonder what else is out there that we just haven't even begun to imagine yet. So we've got these like potential hidden particles, maybe messing with the Higgs boson, changing how we look for it, all that. But this paper goes even further, right? Something about like the universe not being as stable as we thought.
Right, it's called vacuum stability, and it can get pretty complicated. Basically, it's asking, is the universe in its lowest energy state actually stable? Like over, really long periods.
Okay, so is this like finding out that like the ground beneath our feet isn't as solid as we thought? Should we be worried?
It's not quite like that. Think of it this way. Imagine the universe is like a valley, right? And we're down here at the very bottom, the lowest energy state. What this paper is suggesting is that with these fourth-generation particles, there might be other valleys out there, even lower, that are separated by, like, energy barriers.
Okay, so maybe not shaky ground, but more like our valley is on a raft or something floating in this massive ocean, and there might be other valleys out there we just haven't seen yet.
That's a great analogy.
Yeah.
And yeah, this paper suggests that these particles could mean the universe is, well, maybe a little less stable than we thought. But we're talking about timescales that are just mind-bogglingly long. It's not like everything is going to suddenly fly apart.
Okay, that's good to know. But it really shows you how even these, like, super theoretical physics concepts can have these huge implications for how we understand, well, everything, right? The nature of reality itself.
Absolutely. And this paper is a perfect example of how theoretical and experimental physics have to work together. Theorists, they come up with these amazing, sometimes crazy-sounding ideas like a fourth generation of particles. And then it's up to the experimentalists to figure out, okay, how do we actually test this? Can we find evidence to support it?
It's like this constant back and forth, pushing the boundaries of what we know and how we know it. I've got to say, this deep dive has been wild, to say the least.
It's pretty out there.
We started with these hidden particles, ended up talking about the Higgs boson, cosmic camouflage, the stability of the universe. It's a lot.
It really is. But the most exciting thing is that we're just scratching the surface, really. This paper opens up so many more questions than it answers, and that's really what good science is all about.
It is. So let's recap one last time. This paper throws in this idea of a fourth generation of particles. It completely changes how we think the Higgs boson might interact with other particles, how we look for it, and even whether the universe is going to stick around as long as we thought.
Yeah, it's definitely a lot to process. But I think if there's one thing to take away from all this, it's that sometimes the most important discoveries come from exploring even the most outlandish ideas. Who knows what other mysteries the universe is hiding, just waiting for us to uncover them.
That's a great point. And if anyone out there wants to dive into the nitty-gritty themselves, be sure to check out the paper, Four Generations and Higgs Physics. Even if you're not a particle physicist, it's a fascinating read.
And as always, if you come across any other cool research papers, any scientific mysteries you want us to tackle, send them our way. We are always up for a challenge.
Absolutely. So until next time, keep those brains buzzing and never stop questioning the universe around you. This is The Deep Dive, signing off.